After the tone, please.
Welcome to the Is Cloud Computing a Reality for HPC Data Centers webinar. Please note, you may press *1 to ask a live question at the end of the meeting. I would now like to turn the meeting over to Mr. Bill Morris. Please go ahead.
Good day, everyone, and thank you for joining our con call. I'm very pleased to announce that we have Steve Conway, the VP for IDC Research on HPC, going to be speaking for us first and giving some of the background where things are. And then Brad Davidson, a Dell HPC business person, that will give a good explanation of where flexible and dynamic infrastructure becomes a big piece of the equation to run a successful HPC business. And then I'll be speaking as the platform computing CTO on how grid and cloud can work into that equation and where it all fits together. So I think we're about ready to get started. One of the things that we would like to do is there is a text box that you can enter Q&A questions into. We'll try to keep track of that as we're speaking. But at the very end, we'll open up the lines for some Q&A by voice. So, Steve, I'll hand it over to you.
Thanks, Phil. I'll talk today about HPC cloud computing, mostly from the standpoint of buyers and users that IDC deals with. First, our HPC definition, so we're clear about that. We define HPC as requiring modeling or simulation, and it has to take place on a cluster or other server. Desktop computing doesn't qualify. Here are the sources for the perspectives I'll be talking about, so you know where I'm coming from. We've held major sessions on cloud computing in every big geography of the world this year with users and also vendors. We did a major study for the European Commission where we talked with hundreds of people in the European HPC community. And we're just about to publish our latest worldwide study of HPC end users, meaning buyers also, and their requirements and plans, including for cloud computing. So we've already done that research. And this is a short list of more than 100 vendors we've discussed this topic with, and that also includes Dell. We've had quite a few discussions with Dell, and they've kind of helped our perspective as well. And then on the user and buyer side, we've talked with more than 250 sites around the world. This is a sampling. So what is cloud computing? It's still new enough that there's no fully baked consensus definition that everybody agrees with yet, but it's safe to say that it's about enabling the online delivery and consumption of services. It could be IT services, business services, consumer services, scientific and engineering services. People agree at least that far. It's also the latest in a series of distributed computing technologies to come out of the world of HPC and also move into the broader IT world in the last decade. First came clusters that link servers together, then grids that link clusters together, and now people are exploring and adopting cloud computing. So this is an evolutionary process. It's an evolutionary technology. It's heavily based on clusters and other existing technologies, and that's good because people generally like technologies to be revolutionary instead of painfully disruptive. Clusters and grids are great for static demands, and clouds are better for fluctuating and elastic demand. How big is the trend? Not just for HPC, but for cloud computing altogether, it amounted to $16 billion in 2009, about 4% of IT spending. And by 2012, IDC sees this cloud computing going to $42 billion, or 9% of IT spending, so that's serious business. These figures are just for the provisioning part and the support part. They don't include the money people pay to use, for example, public clouds. And whether we're talking about clusters or grids or clouds, in each of those cases you need tightly integrated hardware and software solutions. And, you know, Platform and Dell have been collaborating on clusters for quite a while, and now that collaboration is extending to cloud computing. That's one of the reasons we're here today. Most of cloud computing today happens on the private cloud side. Governments are driving a lot of early cloud adoption. Here are 3 government examples. I'll say a little bit more about CERN later. The NASA Climate Cloud is like the CERN Cloud in that it makes not only data available, but also the application software and the entire compute model. And NERSC's private cloud is available to their scientific user base on a nationwide. So these are big in extent, these clouds. Most, but not all, private clouds exist within the firewalls of the companies or organizations that are using them. A big advantage there is control. You can optimize the use of the resources through scheduling, workload balancing, and so forth, and you can extend or burst out from your corporate environment and still maintain strong control over who can go where and do what. And, of course, you can use your existing staff, assuming they have the time, the extra time. With public clouds, the big advantage isn't so much control as flexibility and elasticity. When you need more capacity, hypothetically with public clouds, there's no limit, but there are issues that I'll get into. Time doesn't permit me to address it today, but there are other types of clouds, such as community clouds, semi-private clouds, and so forth. So as we go around, who's actually adopting cloud technology? Well, the list is pretty much the same on the private and public cloud side, except that the private side is moving along faster, as I said. Governments are pushing hard for both private and public HPC cloud use. Some U.S. government agencies have ordered all their managers to explore cloud computing. In China, the national HPC infrastructure isn't very pervasive yet, although China is constructing big HPC centers at breakneck speed. The government sees private and public clouds as vehicles for spreading HPC use by making it available anywhere in the country, often free of charge, at least for today. The Netherlands is funding public cloud computing to boost economic competitiveness. They're providing it free to industry, including small and medium enterprises. Again, I don't think it'll be free over the long haul, but to help getting it up and running, and they're doing that through the Dutch National Supercomputing Network. Manufacturers use a mix of apps, as you know. Some of them are more communications intensive than others, but these apps typically aren't run at big sizes, mostly fewer than 8 cores. So even if there are some dependencies, it can often make sense to go to private or public cloud computing. Biocodes use considerably more cores on average, about 5,000. But a lot of those codes are not communications intensive, so those jobs, many of them are also a nice fit for the cloud. Digital content folks are using clouds to harvest free desktop cycles for rendering, but some of the larger shops have server-level work that qualifies, at least in IDC's definition, as HPC. One of the oil and gas majors asked IDC this year to research possibilities for moving all of their worldwide seismic work to cloud computing. You know, they're already using SneakerNet, so poor latency isn't necessarily a showstopper for them as far as the initial movement of the data, but data security is imperative. We're also seeing early adoption in industries that use HPC-like modeling on big data, such as in financial services and for high-end business analytics. This slide looks like the one 2 slides ago, but it's more focused on the usage patterns. On the private cloud side, buyers like the fact that they can leverage their existing IT environments to distribute not only data and applications, but in some cases, the native computing environments themselves with all the policy and directives intact. We're seeing people turn to public clouds to handle workloads or portions of workloads that aren't very latency dependent, or that are where the jobs are relatively small, even if there are some dependencies, as in the manufacturing example I cited a little bit earlier. Surge or overload work is another reason for turning to public clouds for Tier 1 organizations, and that surge or overload work comes in 2 forms, predictable and non-predictable. If it's predictable, generally people pay less because this is all done on a risk basis. And SMEs, such as engineering services firms and lots of other smaller firms, are looking to public clouds to avoid having to buy and support their own servers. Clouds can also be great development platforms for pre-staging new applications and services. That happens on both the public side and also on the private side. Users are also going to private and public clouds to access resources that don't exist in the sort of mainstream HPC data center environments, such as faster processors or GPUs and other accelerators, or a different OS, such as Windows, or a different architecture. So the CERN private cloud is worth just a minute or two more. With a large Hadron Collider, CERN's now the #1 center for high-energy physics in the world, as you know, and that collider generates massive volumes of data, 1 petabyte of data per second when it's running, although a small fraction of that needs to be distributed to CERN's scientific clients in Europe and around the world. The biggest client, by the way, is Fermilab near Chicago. CERN and Platform have been actively collaborating, not just to distribute the data, but also the applications and the computing capability needed to run the scientific problems. So the collaboration is around what will be the world's biggest computing cloud, bar none. That's the expectation. And the extremely demanding requirements of CERN's worldwide scientific user community mean that this private cloud is not a vanilla cloud solution. And for that reason, the CERN platform collaboration will almost surely advance the boundaries of cloud computing in ways that should trickle down and across to benefit the mainstream markets for cloud computing. So we're watching that pretty closely. I want to quickly zoom in on China as an example of where some governments are going on the public cloud side. We had a chance to speak directly with Chinese government officials when they asked us to organize a meeting back in October in Beijing. China sees HPC clouds as an important business model, including, and in some ways especially, for regional economic development. The government launched 5 cloud centers this year with free access. They're pushing industrial use as hard as they can. They have some interesting industrial demonstration projects going, but it's just ramping up. The government's providing the service free for now, but they're hoping that once it reaches critical mass, private industry will want to take it over. Here are some key concerns with public clouds today. These really don't apply much, or if at all, on the private cloud side. At the top of the list, seems like for everybody, is data security, which is why many early adopters keep sensitive data away from the cloud. Also, Amazon and others tell us that when many users are firing up their cloud clusters at the same time, it can be a challenge for the cloud providers to keep those clusters segregated, although they're doing it. And also, not all cloud providers can guarantee that they can fully scrub out a client's data if the client leaves the service. Buyers are also concerned about cloud vendor lock-in if they want to change providers, because the cloud platforms are not always interoperable. Some data center managers argue that they can provide the same services on premise for a fraction of the cost of public clouds. Now, part of that has to do with the age-old issue of centralization and decentralization and kind of letting go of portions of workloads. So, but part of it, there's some reality. NASA bids for Amazon cycles on a public auction website and does a lot better than the EC2 list price, but there's a catch. There's a big difference. NASA isn't, for that price, accessing the HPC-oriented EC2 cluster compute instances, each of which includes 2 Nehalem processors and 24 gigabytes of RAM. They're getting something much more vanilla. ISV licensing costs are a buyer concern both on-premise and in the cloud. And buyers tell us that cloud provider warranties are still often too weak. If the provider fails to live up to the terms of the service level agreement, the warranty may pay the customer very little compared to the loss of time and business. So in summary, HPC cloud computing is an early stage market that is a potential good fit for a substantial subset of HPC workloads, including in newer data-intensive segments. The attraction and the adoption patterns vary by vertical depending on the requirements of the applications and the security concerns and so forth, and also by country and global region depending mainly on the maturity of the established HPC infrastructure. Governments in North America, EMEA, and Asia are actively promoting private and public cloud adoption as a way to advance scientific and increasingly also to advance economic competitiveness. And just as software has been a main driver of expanded HPC use at every stage during the past 50 years, it's going to be absolutely critical for driving cloud adoption, as will a tight integration of HPC hardware and software. For that reason, IDC thinks companies like Platform and Dell are in a strong position to accelerate cloud adoption and also to benefit from that acceleration. Thank you.
Thanks a lot, Steve. That was a great summary. We'd like to now move over to Brad from Dell to cover the infrastructure side and how that can be a big play in the equation.
Okay, thank you very much. So my name is Brad Davidson. I'm part of the HPC team at Dell, and I'm a business development manager. And so realistically, one of the things I wanted to start with at the beginning was really to discuss, what is the HPC team at Dell and give you a little bit of background of who we are. The HPC team at Dell is really focused on what we call research computing. We're largely public sector based, working with public institutions, either government or education, and we're trying very hard to collaborate with these institutions in order to develop solutions that are very efficient and very directed at actually getting research done. We're not real big targets for going after the top 500 list. We're really trying to work within the budget realities and the environmental realities that institutions are facing today in terms of budget constraints, people constraints, and all of that in the face of an ever-increasing workload and an expansion in the amount of applications as well as data and work that needs to be retired in this process. So as you look at what we're doing here, you start talking about Dell and how HPC clouds come together, the first thing you need to kind of decide is what does HPC cloud computing mean to Dell particularly? Cloud computing is probably the best example we have today of where we're collaborating with our customers. We're working primarily in the private and community cloud segments, where we're working with institutions or collections of institutions that are trying to find ways to more efficiently either share data, utilize the budgets they have within their institution or their common set of interests, and they're trying to find better ways to effectively get more work done and to get more of the answers that come out of the research shared among more people so that can build upon itself and create a snowball effect in the amount of research that comes out of this dollar spent. From an infrastructure perspective, we're really working to develop a set of tools that can be used across compute as well as storage and infrastructure management that maximizes the efficiency and the flexibility of those platforms. If you look at cloud computing as it is today, cloud computing is really trying to find its footing in the HPC space. You see a number of application-driven clouds that are working very well, a la a MATLAB cloud on the TeraGrid that works out of Cornell. Those types of clouds where you're talking about capacity-driven workflows lend themselves very, very quickly into a cloud-type model. But if you're trying to create a community-based cloud infrastructure, one that can be shared amongst a wide breadth of researchers, you have to start looking at some of the physical aspects of being able to run that hardware, and you need the hardware to be flexible enough to be able to adjust to the workloads. So that flexibility and that ability to build upon itself and scale out as the cloud becomes more popular within the community, those are the types of things that we're focusing on at Dell in order to to build out a better overall solution. One of the things I love about Dell and working at Dell is that we partner extremely well with our partners in this case. And as we're partnering with our customers, we're doing it from a perspective that Dell doesn't feel the need to develop everything and deliver a complete Dell solution without any third-party input. What we're really looking for is partnering with people that we can collaborate with and that can add to the total value of the package. And Platform and Dell's partnership over the last few years has been a fine example of this. We've been partnering and delivering full custom or fully delivered, fully specified cluster solutions to customers in the industry, and now we're moving over toward the cloud space. And if you look at it, Platform is really focusing on their strengths and pulling together a very solid software framework that can go from inside the institution and reach outside of the institution in numerous ways, either be it through physical configuration of hardware from a remote site or through rolling together a virtual infrastructure and being able to issue jobs from virtually anywhere in the world into available hardware. Dell is working on providing complete solutions all the way down to the hardware. If you look at doing cloud computing itself, in the end, there has to be some machines down someplace that need to be run. And in that case, you need a full solution of compute and storage and all of the interconnects put together, tied together in a known good format that is aware of the environment that it's in, and that can be used to be optimized to deliver the most performance for the dollar. This combination of Dell and Platform working together and collaborating over the years to deliver solutions into the cluster market, now working to provide optimized solutions into the cloud market, I think is where you're going to see a lot of benefits from this partnership going forward. Now, if you look at what a cloud concept is to HPC computing at Dell right now, realistically we are looking at a private or community-based, where you have a centralized compute resource that has a set of systems administrators and workload administrators that are located near it and are physically going to be touching that hardware and managing that hardware on a regular basis. Now, as you spread out from this centralized resource, you're going to see that you're going to have local researchers that will be very, very close physically to the cluster and will be operating on the cluster very, very regularly. But you'll also increasingly find that there are collaborative researchers that are remote in nature, but still need to have close physical access that will be running what you would call very standard HPC cluster applications, and need to have that direct access into the cluster itself. And then finally, you're going to see that there's an increasing number, especially at some of the larger institutions, where they're reaching out to many of their satellite institutions and their partner institutions, and they want to be able to provide access to this hardware, this centralized compute resource, to maximize the efficiency and to utilize all the cycles. These remote users are very likely going to be more virtualized based in terms of their application usage and how they're going to be deploying jobs onto the cluster. But with these three segments of researchers and their proximity and their needs, all of these need to be addressed and be taken into consideration as you're putting together a total solution. Now, as you move forward, where does Dell fit into this, and what is Dell bringing to the table? Because if you look at the connections of all of this, by and large, most of this is a software infrastructure piece that Platform is bringing to the table. Dell's piece is really tying together everything on the floor and acting as the primary deliverer of this solution in the end, working with the institutions to build up from the core building blocks to provide the compute infrastructure that we're known very well for, but increasingly we're being asked to move into the storage space. Dell has developed a very strong portfolio of HPC storage, be it low-cost NFS storage or high-performance luster-based storage, all within the Dell portfolio that we can bring together in order to bring a very tightly coupled, very well understood, very well characterized from a performance standpoint, total package of hardware. That combined up with the networking side, where we generally leverage our third-party partners. We tie together InfiniBand clusters and 10 gig infrastructure in order to tie together a very, very tightly coupled and known good platform for building up the hardware side. From the software perspective, Dell's main point in this area is to provide add value in the software space where we have the most impact, and that is really tightly coupling to the hardware for manageability, supportability, and maintainability. Beyond that, we partner with companies like Platform in order to deliver the complete solution set all the way up to the application. So if you take a look at all of these building blocks and you wanted to build an example cluster out of this in order to understand how to deploy and some of the things that you need to understand if you're going to go build an efficient centralized computing infrastructure that is, let's say, cloud capable or cloud usable, the first thing you'd have to do is take a look at what a basic cluster structure would look like. Now, the example I've put together for this call is rather simple in nature, but that simple structure is the key to being able to go from a very small deployment and being able to scale up to a very large deployment. As we're looking at this and as we're working with the customers within the environment of cloud computing, what we're finding is that most people are dipping their toes into cloud computing and want to start off with a very small deployment, be able to run a pilot on that, see how the users embrace it, but then be able to take that same infrastructure and scale up to very large quantities over time without having to have a large either forklift upgrade of any hardware or be able to or to have a large single expenditure as they're going through this in order to do the upgrades. So what we've done is we've actually worked with a building block approach on putting together a design. So within this building block, we've combined all of the aspects you need in order to put together a cluster system. And in the example we have here, we have not only the standard compute elements that Dell would be known for. In this case, we're showing off the PowerEdge C-Series servers, which are our high-density servers that have a very good cost metric that are very sustainable, very easy to maintain and be able to monitor, and combining it up with a GPU chassis. Because as you look at people doing cloud computing today, you have a set of folks that are doing very capacity-driven application work. But increasingly, we're seeing more and more people looking for higher and higher performance capabilities within the cloud. GPU clouds are one of the better examples you're seeing come out of the industry today. And you know, there's 3 or 4 groups across the nation right now that are supplying public versions of a GPU cloud. Now, if you look at an institution and all of the researcher needs that go across an institution, being able to offer the widest breadth of hardware capability is going to be the key to having a successful deployment. So within this compute infrastructure of CPUs connected to GPUs, you want to have the flexibility to allocate and reallocate that capability. And the Dell hardware is providing that capability primarily through the use of our C410X chassis, which allows the allocation and reallocation of GPUs to different nodes within the infrastructure. So that piece and that ability to have the flexibility to change out the hardware infrastructure and to be able to allocate resources to virtual applications and then reallocate other hardware to the physical needs of a researcher very tightly coupled to the cluster are going to be the keys to having a high efficiency system. Also included in this design is a luster-based storage solution to create a small pool of high-performance storage for those applications that need the tight coupling. Lower in the rack, you're going to see InfiniBand switches and 10 gig switches, and all of these are just rounding out the needs in order to be able to have a system that is flexible enough to do very, very high-performance solutions, as well as efficient enough to be able to do virtual systems without having any limitations or bottlenecks in the system. So if you look at the overall ability of this compute design, you've got the compute system, you've got the dynamic reallocation, you've got the efficiency and the flexibility you need within the compute rack, but you've also got the storage performance that is key to many of the applications you're going to see on an HPC side. The biggest thing about having this and combining it up with a platform system is the fact that we've developed a known good architecture that we can actually start tuning some of the VMs in order to get better performance. You've got a known good infrastructure in terms of what resources are there, how close they are to the compute systems, how tightly coupled they are between the file systems and the switching and the compute nodes themselves. This type of a structure and the ability to replicate this compute rack over and over again and scale up each of those particular pieces, be it compute or storage or network bandwidth, is the key to having a system that can take you from a pilot system all the way up to a very high-end production floor deployment. Now, at the center of this is what we call a management building block. And in this case, you're really only going to have one of these pieces. The lead piece of this would be the management servers, which would be the main access point for connecting through from a platform external infrastructure to an internal infrastructure and back and forth. Also in this are going to be what we would call login nodes, which give the local researchers and the remote researchers that need that physical connection the ability to log into the cluster, to do individual work on the cluster, interactive work on the cluster without stomping all over each other within the system. Below that is really the remaining infrastructure that tie together the pieces, the Lustre metadata server, which you would need one of to control any number of OSS nodes within the compute racks, as well as the core switching infrastructure. Now, combining all of these pieces together, you have a finalized solution which gives you a full standard infrastructure that is scalable across all of the points that give you the ability to grow as you go. The flexibility of this infrastructure that allows for dynamic reconfiguration of the resources based on the workload that's coming in. The platform software is going to have the ability, and through the collaboration with Dell, we're building upon that ability to be able to control these resources so that you'll have more flexibility and more ability to have fine-grained decisions on what resources get deployed into what application, and to be able to control the workflow and the priority of the queues. So this overall system provides you a very solid platform for being able to have the consistency you need to have the ability to go to your researchers and say that the cloud resources we're providing to you are actually going to deliver the performance that you need. You're going to have that confidence by the tight coupling of the two systems from platform and from Dell. And in summary on this, what you're looking at is Dell is again continuing to build on this solution space. We're working to provide additional functionality into the storage side, as well as additional functionality on the software side to allow a more manageable infrastructure. The architectural consistency of building up a system that is known good with known pieces that are performance rated and that the performance profile is understood within the environment is going to be the keys of being able to migrate successfully from early stage pilot runs all the way through production stages. And the ability of Dell and platform to combine and collaborate and work with you and work with your researchers to overcome the obstacles that you're going to find in this process is going to be the key to having early success in a cloud environment. It's still early days in cloud. We're seeing very good results and very good potential out of this, but we're still at a point now where we need to have close collaboration and the ability to work together. And you need to know that the partners that you're working with are committed to seeing the overall deployment work well and meet the research goals that you have for your institution. And so with that, I'd like to turn it over to Phil.
Great. Thanks for that overview, Brad. That was a really good view into what's going on for both private cloud or dynamic HPC management, how things are changing, and especially with GPU technologies that people are so interested in now. So from that perspective, I'll move to the platform computing view. And, platform has been around and in business for over 18 years. We're best known, of course, for clusters and grids. A lot of capabilities and challenges have been overcome there in terms of resource awareness, workload management, prioritization, et cetera. And the real thing that's happening now is the addition of capabilities around making it more dynamic, more flexible, recognizing additional resources such as GPUs as we move into the future. What we're looking at is a pretty large stack of capabilities where we have entire suites of products called Platform HPC, which includes the core workload management as well as some monitoring capabilities, MPI capabilities, et cetera. Large dedicated grids that a number of very large customers use in a number of ways, both for batch workloads with Platform LSF as well as near real-time SOA-type workloads with Platform Symphony, primarily in the financial services space. And all that's now moving into a cloud management infrastructure as well. And of course, with our background in clusters and grids, our cloud management is going to be dedicated towards really how do you do that with both HPC and the enterprise side in mind. So one of the key points is you have to be able to manage the physical resources as part of the cloud as well as the virtual resources. Quite a few customers and partners that we work with, and of course with Dell as a key partner up in the strategic partner space. So where is this going? One of the key market trends that we're really looking at is extending HPC to the cloud paradigm, and in fact, it's a journey. What we really are seeing is that a few customers are jumping directly towards cloud to make better use of capabilities or functions, especially if they have workloads that are fairly loosely coupled or embarrassingly parallel. Life sciences space has a lot of codes like that, you know, massively parallel blast codes, et cetera. Monte Carlo simulations are fairly massively parallel. And they're pretty easy to put into a cloud paradigm. You put them on a VM resource, and the 2 to 3% overhead of the VM on CPU and memory, it tends to kind of disappear into the background, and you can get near infinite resources. You can dramatically increase the utilization of your resources. However, most codes aren't like that. Most codes actually are somewhat tightly clustered or very tightly clustered, using MPI type capabilities, or they at least have some kind of internode traffic that has to be taken into consideration, and those don't live in a direct cloud paradigm immediately. So one of the things that we do see as the journey is, first of all, just experimenting with VMs, going from purely physical resources to physical plus VM resources, where in the HPC world, the VMs aren't necessarily adding utilization capabilities of the servers. In fact, many grids are already running at 80+% utilization. What they do add is capabilities around suspend resume that HPC codes have never really had a good handle on before. Ability to have a number of low priority jobs all clustered onto one big server, and then when a high priority job comes in that needs either that big memory or big GPU capability of that server, those low priority jobs via VM technology can be moved off, continue running, and then that node can be rededicated to that high priority job. A number of good capabilities get introduced by allowing VMs to have a place in your HPC paradigm, and you need to be able to manage both those physical and virtual resources, and that's really where the private cloud for HPC is coming from. From that, you can then look at what is the capability to integrate larger infrastructure into your private cloud, not just the HPC side, but now possibly integrating in your HPC plus your enterprise apps to generate even better return on investment. And then finally, being able to burst out to some kind of public cloud, making use of resources that can be fairly low cost, although not always lower cost than your internal data center, but fairly low cost, easy to consume, quick to release, and it can be used for jobs that don't have the very high SLA requirements of your internal jobs. Another key piece of that, though, is you have to be able to monitor, manage, analyze, and report on your capabilities, or you really don't have a good handle on who's using what the priorities are, how people are going to be maybe cross-charged for it, or even if you're not cross-charging, just have a good understanding of what your capacity planning and management is going to look at in moving in the future. Of course, we've mentioned GPUs. That's become a big piece of HPC landscapes. All the new supercomputers are trending in that direction. But as well, we're finding a lot of smaller grids are using a few of them to accelerate certain codes. In the manufacturing space, there's partners like Simulia and Ansys that are doing a lot of work that take advantage of GPUs. In seismic space, there's a fair amount going on there as well. Financial services space, et cetera. Another thing is ISV application integration. As Steve mentioned earlier, you really need to figure out if your ISV application can live in a floating cloud type environment. If it's a node locked entity, or especially if it has a dongle or something like that, letting that live in, even on a VM is very difficult to achieve, much less living in a private or public cloud. So the typical types of challenges, users versus IT, and there's always the question of, is this going to get thrown over the wall, or do you allow for these guys to work together? Because they do have different needs, right? The users want more grid resources, they want to run their applications faster, they want flexible capabilities to allow them to bring up new lines of business or new ways of attacking a problem. And of course, if they're being cross-charged, they want better cost performance. IT, though, they're charged with the SLA management, which is usually much more tightly managed than a public cloud like Amazon EC2. And so they have to not only contain costs and allow for performance, but they have to handle all the uptime, reliability, availability needs, and be able to do that management and reporting on those availabilities. Of course, they're handling the security infrastructure, mapping capabilities as needed, growing things, changing, and really keeping that whole infrastructure up and running, but feeding the users with more flexible resources. So what that's driving is that some type of or form of cloud computing, or at least first steps along that path with virtualization. So there's the possibility of having a dedicated HPC cluster with then maybe a private cloud off to the side that resources could be brought in to the HPC cluster as needed, and otherwise be available to other parts of the business when it's not being used for HPC. Again, with the knowledge around what the SLAs are, especially if it's performance SLAs, tightly coupled codes, et cetera. Also, letting small groups get up and running very quickly. Instead of giving them a dedicated cluster, allowing them to do some initial exploration on some dynamic flexible resources that maybe have higher SLAs for performance than a public cloud provider, such as better internode bandwidth, high speed storage capabilities like Brad talked about with Luster, those kind of things that would allow them to run very good speeds, not up to maybe the absolute physical speeds, but at least get their acceleration started. And of course, not all workload is suitable for cloud at all. There's quite a few things that do work, but there's an even bigger list of things that don't work. And there's still a lot of question in the HPC community about, is cloud ever going to be appropriate for their use case? So high energy physics was pushing in that direction, and now CERN's breaking that boundary and really doing a lot of investigation about what could be done with cloud, especially cloud that allows them to manage both physical and virtual resources. So our approach is, there's product plus service plus public or private cloud resources that can be called upon to eventually give you the total application solution with the SLAs, with the capabilities, the performance metrics that you need, the availability metrics that you need, ability to maybe suspend and resume if that's a part of your SLA. All those kind of things need to come into the puzzle. And as Brad said, you really need to look at this end to end, how it all works together, all the pieces, and can the physical pieces be somewhat dynamic in infrastructure as well, thus allowing you even more flexibility, more dynamic control while meeting your performance needs. There's a good online question that came up: is cloud computing a natural extension of HPC? Is there a case where mainstream IT is completely based on cloud computing? This webcast is not about mainstream IT, so I'm not going to try to approach that one. I may let Steve Conway answer that at the very end. But is cloud computing a natural extension of HPC? It is, in some ways, a natural extension. If you think of a large grid, it already has many of the features and functionality of what we consider cloud computing at this point. Very high utilization, ability to handle multiple workloads, ability to handle many, many users, submitting workloads all the time, a somewhat dynamic infrastructure, although it's been generally thought of as fairly static in the past, but it's really been somewhat fungible for the last 4 or 5 years. Anything from being able to reallocate resources on the storage side or on the network side to various nodes in the compute grid. So yeah, it is definitely a natural extension, but there's also a number of pieces that people think of with cloud computing that don't necessarily fit well within the HPC space. So our product line, what we're looking at, the HPC suite or LSF and MPI, with the ISF, which is our infrastructure sharing facility, which is our basically our cloud management middleware, all come together to be able to solve the problem. And the way that that's done is we have a lower level capability that they're all built upon called EGO that allows recognition of resources, physical, virtual, GPU, even external cloud-based providers, and that's a plug-in that allows all these pieces to do the extension and capabilities. So what is it? It's a dynamic resource management. It's your typical IaaS stack, private cloud management stack, with lots of pieces that plug into it, VM management, hardware provisioning, server storage, network capabilities, lots of plugins for third parties, since many customers already have provisioning management systems, virtual management systems in place. We just plug and play as needed. Also with some security capabilities like single sign-on, pluggable authentication modules, etc. even custom integrations with CMDBs to make sure that change management items are kept track of, etc. Another big area is what we call cloud bursting, and make it easy to extend to a cloud, whether that's a private cloud or an external cloud. A private cloud very often on customer sites is usually started in the main enterprise data center, not necessarily the HPC data center or HPC side of the house. And so it's possible to actually borrow resources out of that private cloud as well. So the three ways that we see it is a fully integrated cluster with the cloud, where the external resources look pretty much as if they are part of the built-in cluster. Multi-cluster, where you build a second cluster or a third cluster or a fourth cluster out in the cloud-based services. And then a dynamic extension where you're using both products together, the grid cluster management software as well as the private cloud management software. So a couple of use cases to go through real quick. Integrating directly into it. If you have your internal resources and they're fairly full, which is what all the red blocks indicate, and you still have more jobs coming in, there could be a policy-based control, the block up on the far right, that is working with the platform LSF that says, hey, there's some kind of cloud resources available, whether that's public or private, and you want to be able to borrow from that. So the policy determines that some part of these jobs is allowed to be extended out to this cloud-based resource because by policy there may be lower priority or they don't have performance SLAs around them, whatever the case may be. The LSF launches a script that asks for those resources to be allocated, and in this example it's pulling from an external cloud, EC2, and those resources then get pulled in, and in this case it's coming in over a VPC so that the resources are within the same IP address boundaries. They already have AMIs that have platform LSF on them, and they boot up and get introduced into the internal resources and indeed look like they're part of the internal grid, but there's resource controls around them that says we know that these aren't actually internal and there's going to be policy rules that only certain applications can be built upon there. Use case number 2, multi-cluster. Again, you have resources coming in, jobs coming in that are overwhelming the internal resources. The LSF goes off and asks, runs a script to ask for more resources to be dedicated. But now we have this multi-cluster orchestrator that is run, and in this case, an entirely new grid is brought up with its own master and slave nodes, and then the jobs that are allowed to go out to this secondary grid go through multi-cluster orchestrator and are put there as appropriate. And multi-cluster orchestrator will do its best to balance the workload, but within the policy boundaries that have been established. And finally, a dynamic cluster extension to the cloud, where you have ISF now doing all the policy management, and it can much more seamlessly, instead of just running a script, it has direct integration into both the private cloud that it's running as well as public cloud such as Amazon EC2. And so as it goes through and it does the work, it passes those resources back to platform LSF that then can run the workload on there. And so that could be the entire workload running out on the cloud. It could be a new grid running out on the cloud. It could be an extension of resources. Any of those are possible through this mechanism. So overall summary, you have to design for extensibility and scalability, flexibility, which I think Brad made a really good set of points around. On-demand scalability, be able to grow and shrink when needed, and to contain capital costs, keeping utilization fairly high. And then, of course, it has to have, top-level support. If you have any problems, you need to be able to have a single phone call fix that problem and not have a bunch of people pointing fingers at each other or have to solve your own problems through open source unless you have a very large staff available to do that. So that will end the formal presentation. We have a couple of minutes for open Q&A. If we could open the lines.
Certainly. Once again, please press *1 at this time if you have a question. There will be a brief pause while the participants register. Thank you for your patience.
And Steve, while we're waiting for them, did you want to address maybe is mainstream IT going to be completely based on cloud computing? Do you see that as a trend?
Well, I see it as a trend that it's going to be increasingly cloud computing will be important. I think, what we see is that over time, the distinction between the kind of resident data center, the private cloud extension, and the public cloud, those distinctions are going to become less and less meaningful. Ultimately, I think that what's going to be possible even in public clouds is to replicate, pretty faithfully replicate what's being done on premise, and the big difference is going to be one of economics. How much do you want to put and pay for on your own floor versus have somebody else take care of for you?
Right. Operator, do we have any questions?
There are no questions registered at this time.
All right. Well, we're about at the top of the hour, so I really want to thank you, Steve and Brad, for participating with us, and we'll go ahead and close this call.
Thank you.
Thank you very much.